the search result object catalog with search criteria and query str and receives books of type list of book. Creates a search result object with books. Converts the search result object to a JSON string. What about other endpoints? For instance, those allowing librarians to add book items through /add-book-item. Theo would have to repeat the exact same process and create 3 classes. Add book item controller to handle a query, book item query to convert the JSON query string into data, book item result to convert the search result data into a JSON string. The code that deals with JSON deserialization that Theo wrote previously in search query would have to be rewritten in book item query. Same thing for the code that deals with JSON serialization he wrote previously in search result. It would have to be rewritten in book item result. The bad news is that Theo would have to repeat the same process for every endpoint of the system. Each time he encounters a new kind of JSON input or output, he would have to create a new class and write code. Theo's dream is turning into a nightmare. Suddenly, his phone rings, next to where he was resting his head on the desk. As Theo wakes up, he realizes that Nancy never asked for JSON. It was all a dream, a really bad dream. Tip: in OOP, data serialization is difficult. It's quite frustrating that handling JSON serialization and deserialization in OOP requires the addition of so many classes and writing so much code, again and again. The frustration grows when you consider that serializing a search query, a book item query, or any query is quite similar. It comes down to going over data fields, concatenating the name of the data fields and the value of the data fields separated by a comma. Why is such a simple thing so hard to achieve in OOP? In OOP, data has to follow a rigid shape defined in classes, which means that data is locked in members. There is no simple way to access data generically. Tip: in OOP, data is locked in classes as members. We will refine later what we mean by generic access to the data, and we will see how DOP provides a generic way to handle JSON serialization and deserialization. Until then, you will have to continue suffering. But at least you are starting to become aware of this suffering, and you know that it is avoidable. Note: most OOP programming languages alleviate a bit of the difficulty involved in the conversion from and to JSON. It either involves reflection, which is definitely a complex thing, or code verbosity. Section 1.2.4 Complex Class Hierarchies. One way to avoid writing the same code twice in OOP involves class inheritance. Indeed, when every requirement of the system is known up front, you design your class hierarchy in such a way that classes with common behavior derive from a base class. Figure 1.15 shows an example of this pattern that focuses on the part of our class diagram that deals with members and librarians. Both librarians and members need the ability to log in, and they inherit this ability from the user class. So far, so good. But when new requirements are introduced after the system is implemented, it's a completely different story. Fast forward to Monday, March 29th at 11 a.m., where 2 days are left before the deadline, Wednesday at midnight. Nancy calls Theo with an urgent request. Theo is not sure if it's a dream or reality. He pinches himself and he can feel the jolt. It's definitely reality. Nancy: how is the project doing? Theo: fine, Nancy. We're on schedule to meet the deadline. We're running our last round of regression tests now. Nancy: fantastic. It means we have time for adding a tiny feature to the system, right? Theo: depends what you mean by tiny. Nancy: we need to add VIP members to the system. Theo: what do you mean by VIP members? Nancy: VIP members are allowed to add book items to the library by themselves. Theo: Nancy: what? Theo: That's not a tiny change. Nancy: Why? I'll ask you the same question Nancy asked Theo. Why is adding VIP members to our system not a tiny task? After all, Theo has already written the code that allows librarians to add book items to the library. It's in librarian : add book item. What prevents him from reusing this code for VIP members? The reason is that in OOP, the code is locked into classes as methods. Tip: in OOP, code is locked into classes. VIP members are members that are allowed to add book items to the library by themselves. Theo decomposes the customer requirements into two pieces. VIP members are library members. VIP members are allowed to add book items to the library by themselves. Theo then decides that he needs a new class, VIP member. For the first requirement, VIP members are library members, it seems reasonable to make VIP member derive from member. However, handling the second requirement, VIP members are allowed to add book items, is more complex. He cannot make a VIP member derive from librarian because the relation between VIP member and librarian is not linear. On one hand, VIP members are like librarians in that they are allowed to add book items. On the other hand, VIP members are not like librarians in that they are not allowed to block members or list the books lent to a member. The problem is that the code that adds book items is locked in the librarian class. There is no way for the VIP member class to use this code. Figure 1.16 shows one possible solution that makes the code of librarian : add book item available to both librarian and VIP member classes. Here are the changes to the previous class diagram. A base class, user with book item right, extends user. Add book item moves from librarian to user with book item right. Both VIP member and librarian extend user with book item right. It wasn't easy, but Theo manages to handle the change on time, thanks to an all-nighter coding on his laptop. He was even able to add new tests to the system and run the regression tests again. However, he was so excited that he didn't pay attention to the diamond problem VIP member introduced in his class diagram due to multiple inheritance. VIP member extends both member and user with book item right, which both extend user. Wednesday, March 31st at 10 a.m., 14 hours before the deadline, Theo calls Nancy to tell her the good news. Theo: We were able to add VIP members to the system on time, Nancy. Nancy: Fantastic! I told you it was a tiny feature. Theo: Yeah, well. Nancy: Look, I was going to call you anyway. I just finished a meeting with my business partner and we realized that we need another tiny feature before the launch. Will you be able to handle it before the deadline? Theo: Again, it depends what you mean by tiny. Nancy: We need to add super members to the system. Theo: What do you mean by super members? Nancy: Super members are allowed to list the books lent to other members. Theo: Nancy: What? Theo: That's not a tiny change. Nancy: Why? As with VIP members, adding super members to the system requires changes to Theo's class hierarchy. Figure 1.17 shows the solution Theo has in mind. The addition of super members has made the system really complex. Theo suddenly notices that he has 3 diamonds in his class diagram, not gemstones, but 3 deadly diamonds of death, as OOP developers sometimes name the ambiguity that arises when a class D inherits from 2 classes B and C, where both inherit from class A. He tries to avoid the diamonds by transforming the user class into an interface and using the composition over inheritance design pattern, but with the stress of the deadline looming, he isn't able to use all of his brain cells. In fact, the system has become so complex, he's unable to deliver the system by the deadline. Theo tells himself that he should have used composition instead of class inheritance, but it's too late now. Tip: In OOP, prefer composition over class inheritance. At 10 p.m., 2 hours before the deadline, Theo calls Nancy to explain the situation. Theo: Look, Nancy, we really did our best, but we won't be able to add super members to the system before the deadline. Nancy: No worries, my business partner and I decided to omit this feature for now. We'll add it later. With mixed feelings of anger and relief, Theo stops pacing around his office. He realizes he will be spending tonight in his own bed rather than plowing away on his computer at the office. That should make his wife happy. Theo: I guess that means we're ready for the launch tomorrow morning. Nancy: Yes, we'll offer this new product for a month or so, and if we get good market traction, we'll move forward with a bigger project. Theo: Cool. Let's be in touch in a month then. Good luck on the launch. Summary. Complexity in the context of this book means hard to understand. We use the terms code and behavior interchangeably. DOP stands for Data-Oriented Programming. OOP stands for Object-Oriented Programming. FP stands for Functional Programming. In a composition relation where one object dies, the other one also dies. A composition relation is represented by a plain diamond at one edge and an optional star at the other edge. In an association relation, each object has an independent life cycle. A many-to-many association relation is represented by an empty diamond and a star at both edges. Dashed arrows indicate a usage relation, for instance, when a class uses a method of another class. Plain arrows with empty triangles represent class inheritance, where the arrow points towards the superclass. The design presented in this chapter doesn't pretend to be the smartest OOP design. Experienced OOP developers would probably use a couple of design patterns and suggest a much better diagram. Traditional OOP systems tend to increase system complexity, in the sense that OOP systems are hard to understand. In traditional OOP, code and data are mixed together in classes, data as members and code as methods. In traditional OOP, data is mutable. The root cause of the increasing complexity is related to the mixing of code and data together into objects. When code and data are mixed, classes tend to be involved in many relations. When objects are mutable, extra thinking is required in order to understand how the code behaves. When objects are mutable, explicit synchronization mechanisms are required on multi-threaded environments. When data is locked in objects, data serialization is not trivial. When code is locked in classes, class hierarchies tend to be complex. A system where every class is split into two independent parts, code and data, is simpler than a system where code and data are mixed. A system made of multiple simple independent parts is less complex than a system made of a single complex part. When data is mutable, code is unpredictable. A strategic use of design patterns can help mitigate complexity in traditional OOP to some degree. Data immutability brings serenity to DOP developers' minds. Most OOP programming languages alleviate slightly the difficulty involved in the conversion from and to JSON. It either involves reflection, which is definitely a complex thing, or code verbosity. In traditional OOP, data serialization is difficult. In traditional OOP, data is locked in classes as members. In traditional OOP, code is locked into classes. DOP reduces complexity by rethinking data. DOP is compatible both with OOP and FP. Chapter 2. Separation between code and data. A whole new world. This chapter covers the benefits of separating code from data, designing a system where code and data are separate, implementing a system that respects the separation between code and data, The first insight of DOP is that we can decrease the complexity of our systems by separating code from data. Indeed, when code is separated from data, our systems are made of two main pieces that can be thought about separately: data entities and code modules. This chapter is a deep dive in the first principle of DOP, summarized in Figure 2.1. Principle number 1. Separate code from data such that the code resides in functions, whose behavior doesn't depend on data that is somehow encapsulated in the function's context. In this chapter, we'll illustrate the separation between code and data in the context of Claphem's library management system that we introduced in Chapter 1. We'll also unveil the benefits that this separation brings to the system. The system is simple. It is easy to understand. The system is flexible and extensible. Quite often, it requires no design changes to adapt to changing requirements. This chapter focuses on the design of the code in a system where code and data are separate. In the next chapter, we'll focus on the design of the data. As we progress in the book, we'll discover other benefits of separating code from data. Section 2.1. The two parts of a DOP system. While Theo is driving home after delivering the prototype, he asks himself whether the Claphem project was a success or not. Sure, he was able to satisfy the customer, but it was more luck than brains. He wouldn't have made it on time if Nancy had decided to keep the super members feature. Why was it so complicated to add tiny features to the system? Why was the system he built so complex? He thought there should be a way to build more flexible systems. The next morning, Theo asks on Hacker News and on Reddit for ways to reduce system complexity and build flexible systems. Some folks mention using different programming languages, while others talk about advanced design patterns. Finally, Theo's attention gets captured by a comment from a user named Joe. He mentions data-oriented programming and claims that its main goal is to reduce system complexity. Theo has never heard this term before. Out of curiosity, he decides to contact Joe by email. What a coincidence! Joe lives in San Francisco too. Theo invites him to a meeting in his office. Joe is a 40-year-old developer. He was a Java developer for nearly a decade before adopting Clojure around 7 years ago. When Theo tells Joe about the library management system he designed and built, and about his struggles to adapt to changing requirements, Joe is not surprised. Joe tells Theo that the systems that he and his team have built in Clojure over the last 7 years are less complex and more flexible than the systems he used to build in Java. According to Joe, the systems they build now tend to be much simpler because they follow the principles of DOP. Theo: I've never heard of data-oriented programming. Is it a new concept? Joe: Yes and no. Most of the foundational ideas of data-oriented programming, or DOP as we like to call it, are well known to programmers as best practices. The novelty of DOP, however, is that it combines best practices into a cohesive whole. Theo: That's a bit abstract for me. Can you give me an example? Joe: Sure. Take, for instance, the first insight of DOP. It's about the relations between code and data. Theo: You mean the encapsulation of data in objects? Joe: Actually, DOP is against data encapsulation. Theo: Why is that? I thought data encapsulation was a positive programming paradigm. Joe: Data encapsulation has both merits and drawbacks. Think about the way you designed the library management system. According to DOP, the main cause of complexity and inflexibility in systems is that the code and data are mixed together in objects. Tip: DOP is against data encapsulation. Theo: It sounds similar to what I've heard about functional programming. So, if I want to adopt DOP, do I need to get rid of object-oriented programming and learn functional programming? Joe: No, DOP principles are language-agnostic. They can be applied in both object-oriented and functional programming languages. Theo: That's a relief. I was afraid that you were going to teach me about monads, algebraic data types, and higher-order functions. Joe: No, none of that is required in DOP. Tip: DOP principles are language-agnostic. Theo: what does the separation between code and data look like in DOP then? Joe: data is represented by data entities that only hold members. Code is aggregated into modules where all functions are stateless. Theo: what do you mean by stateless functions? Joe: instead of having the state encapsulated in the object, the data entity is passed as an argument. Theo: I don't get that. Joe: here, let's make it visual. Joe steps up to a whiteboard and quickly draws a diagram to illustrate his comment. Figure 2.2 shows Joe's drawing. Theo: it's still not clear. Joe: it will become clearer when I show you how it looks in the context of your library management system. Theo: okay, shall we start with code or with data? Joe: well, it's data-oriented programming, so let's start with data. Section 2.2, Data Entities. In DOP, we start the design process by discovering the data entities of our system. Here's what Joe and Theo have to say about data entities. Joe: what are the data entities of your system? Theo: what do you mean by data entities? Joe: I mean the parts of your system that hold the information. Note: data entities are the parts of your system that hold information. Theo: well, it's a library management system, so we have books and members. Joe: of course, but there are more. One way to discover the data entities of a system is to look for nouns and noun phrases in the requirements of the system. Theo looks at Nancy's requirement napkin. He highlights the nouns and noun phrases that seem to represent data entities. Highlighting terms in the requirements that correspond to data entities. There are two kinds of users: library members and librarians. Users log into the system via email and password. Members can borrow books. Members and librarians can search books by title or by author. Librarians can block and unblock members, for example, when they are late in returning a book. Librarians can list the books currently lent to a member. There could be several copies of a book. Joe: excellent. Can you see a natural way to group these entities? Theo: not sure, but it seems to me that users, members, and librarians form one group, whereas books, authors, and book copies form another group. Joe: sounds good to me. What would you call each group? Theo: probably user management for the first group and catalog for the second group. The data entities of the system organized in a nested list. The catalog data. Data about books. Data about authors. Data about book items. Data about book lendings. The user management data. Data about users. Data about members. Data about librarians. Theo: I'm not sure about the relations between books and authors. Should it be association or composition? Joe: don't worry too much about the details for the moment. We'll refine our data entity design later. For now, let's visualize the two groups in a mind map. Theo and Joe confer for a bit. Figure 2.3 shows the mind map they come up with. The most precise way to visualize the data entities of a DOP system is to draw a data entity diagram with different arrows for association and composition. We will come back to data entity diagrams later. Tip: discover the data entities of your system and then sort them into high-level groups, either as a nested list or as a mind map. We will dive deeper into the design and representation of data entities in the next chapter. For now, let's simplify things and say that the data of our library system is made of two high-level groups: user management and catalog. Section 2.3, Code Modules. The second step of the design process in DOP is to define the code modules. Let's listen in on Joe and Theo again. Joe, now that you have identified the data entities of your system and have arranged them into high-level groups, it's time to think about the code part of your system. Theo, what do you mean by the code part? Joe, one way to think about that is to identify the functionality of your system. Theo looks again at Nancy's requirements. This time, he highlights the verb phrases that represent functionality, highlighting terms in the requirements that correspond to functionality. There are two kinds of users, library members and librarians. Users log in to the system via email and password. Members can borrow books. Members and librarians can search books by title or by author. Librarians can block and unblock members, for example, when they are late in returning a book. Librarians can list the books currently lent to a member. There could be several copies of a book. In addition, it's obvious to Theo that members can also return a book. Moreover, there should be a way to detect whether a user is a librarian or not. He adds those to the requirements and then lists the functionality of the system. The functionality of the library system. Search for a book. Add a book item. Block a member. Unblock a member. Log a user into the system. List the books currently lent to a member. Borrow a book. Return a book. Check whether a user is a librarian. Joe, excellent. Now, tell me what functionality needs to be exposed to the outside world. Theo, what do you mean by exposed to the outside world? Joe, imagine that the library management system exposes an API over HTTP. What functionality would be exposed by the HTTP endpoints? Theo, well, all system functionality would be exposed, except checking to see if a user is a librarian. Joe, okay, now give each exposed function a short name and gather them together in a module box called library. That takes Theo less than a minute. Figure 2.4 shows the module that contains the exposed functions of the library devised by Theo. Tip. The first step in designing the code part of a DOP system is to aggregate the exposed functions into a single module. Joe, beautiful! You just created your first code module. Theo, to me it looks like a class. What's the difference between a module and a class? Joe, a module is an aggregation of functions. In OOP, a module is represented by a class, but in other programming languages, it might be a package or a namespace. Theo, I see. Joe, the important thing about DOP code modules is that they contain only stateless functions. Theo, you mean like static methods in Java? Joe, yes, and the classes of these static methods should not have any data members. Theo, so how do the functions know what piece of information they operate on? Joe, easy. We pass that as the first argument to the function. Theo, okay, can you give me an example? Joe, biting his nails, takes a look at the list of functions of the library module in Figure 2.4. He spots a likely candidate. Joe, let's take, for example, get book lendings. In classic OOP, what would its arguments be? Theo, a librarian ID and a member ID. Joe, so in traditional OOP, get book lendings would be a method of a library class that receives two arguments, librarian ID and member ID. Theo, yep. Joe, now comes the subtle part. In DOP, get book lendings is part of the library module, and it receives the library data as an argument. Theo, could you show me what you mean? Joe, sure. Joe goes over to Theo's keyboard and starts typing. He enters an example of what a class method looks like in OOP. Theo: right. The method accesses the state of the object, in our case the library data, via this. Joe: would you say that the object's state is an argument of the object's methods? Theo: I'd say that the object's state is an implicit argument to the object's methods. Tip: in traditional OOP, the state of the object is an implicit argument to the methods of the object. Joe: well, in DOP, we pass data as an explicit argument. The signature of getBookLendings would look like this. Joe: the state of the library is stored in library data, and library data is passed to the getBookLendings static method as an explicit argument. Theo: is that a general rule? Joe: absolutely. The same rule applies to the other functions of the library module, and to other modules as well. All of the modules are stateless. They receive the library data that they manipulate as an argument. Tip: in DOP, functions of a code module are stateless. They receive the data that they manipulate as an explicit argument, which is usually the first argument. Note: a module is an aggregation of functions. In DOP, the module functions are stateless. Theo: it reminds me of Python and the way the self argument appears in method signatures. Here, let me show you an example. Joe: indeed, but the difference I'm talking about is much deeper than a syntax change. It's about the fact that data lives outside the modules. Theo: I got that. As you said, module functions are stateless. Joe: exactly. Would you like to try and apply this principle across the whole library module? Theo: sure. Theo refines the design of the library module by including the details about the function's arguments. He presents the diagram in figure 2.5 to Joe. Joe: perfect. Now we're ready to tackle the high-level design of our system. Theo: what's a high-level design in DOP? Joe: a high-level design in DOP is the definition of modules and the interaction between them. Theo: I see. Are there any guidelines to help me define the modules? Joe: definitely. The high-level modules of the system correspond to the high-level data entities. Theo: you mean the data entities that appear in the data mind map? Joe: exactly. Theo looks again at the data mind map, figure 2.6. He focuses on the high-level data entities library, catalog, and user management. This means that in the system, besides the library module, we have two high-level modules. The catalog module deals with catalog data. The user management module deals with user management data. Theo then draws the high-level design of the library management system with the catalog and user management modules. Figure 2.7 shows the addition of these modules, where functions of catalog receive catalog data as their first argument. Functions of user management receive user management data as their first argument. It's not 100% clear for Theo at this point how the data entities get passed between modules. For the moment, he thinks of library data as a class with two members. Catalog holds the catalog data. User management holds the user management data. Theo also sees that the functions of library share a common pattern. Later on in this chapter, we'll see the code for some functions of the library module. They receive library data as an argument. They pass library data.catalog to the functions of catalog. They pass library data.usermanagement to the functions of user management. Tip: the high-level modules of a DOP system correspond to the high-level data entities. Section 2.4. DOP systems are easy to understand. Theo takes a look at the two diagrams that represent the high-level design of his system. The data entities in the data mind map in figure 2.8. the code modules in the module diagram in Figure 2.9. A bit perplexed, Theo asks Joe, "Theo, I'm not sure that this system is better than a traditional OOP system where objects encapsulate data." Joe, "The main benefit of a DOP system over a traditional OOP system is that it's easier to understand." Theo, "What makes it easier to understand?" Joe, "The fact that the system is split cleanly into code modules and data entities." Theo, "How does that help?" Joe, "When you try to understand the data entities of the system, you don't have to think about the details of the code that manipulates the data entities." Theo, "So when I look at the data mind map of my library management system, I can understand it on its own?" Joe, "Exactly. And similarly, when you try to understand the code modules of the system, you don't have to think about the details of the data entities manipulated by the code. There is a clear separation of concerns between the code and the data." Theo looks again at the data mind map in Figure 2.8. He has kind of an aha moment. Data lives on its own. Note: a DOP system is easier to understand because the system is split into two parts, data entities and code modules. Now, Theo looks at the module diagram in Figure 2.9. He feels a bit confused and asks Joe for clarification. On one hand, the module diagram looks similar to the class diagrams from classic OOP, boxes for classes and arrows for relations between classes. On the other hand, the code module diagram looks much simpler than the class diagrams from classic OOP, but he cannot explain why. Theo, "The module diagram seems much simpler than the class diagrams I'm used to in OOP. I feel it, but I can't put it into words." Joe, "The reason is that module diagrams have constraints." Theo, "What kind of constraints?" Joe, "Constraints on the functions we saw before. All the functions are static or stateless, but there's also constraints on the relations between the modules." Tip: all the functions in a DOP module are stateless. Theo, "In what way are the relations between modules constrained?" Joe, "There is a single kind of relation between DOP modules, the usage relation. A module uses code from another module. There's no association, no composition, and no inheritance between modules. That's what makes a DOP module diagram easy to understand." Theo, "I understand why there is no association and no composition between DOP modules. After all, association and composition are data relations. But why no inheritance relation? Does that mean that DOP is against polymorphism?" Joe, "That's a great question. The quick answer is that in DOP, we achieve polymorphism with a different mechanism than class inheritance. We will talk about it someday. Note: for a discussion of polymorphism in DOP, see Chapter 13. Theo, "Now you've piqued my curiosity. I thought inheritance was the only way to achieve polymorphism." Theo looks again at the module diagram in Figure 2.9. Now he not only feels that this diagram is simpler than traditional OOP class diagrams, he understands why it's simpler. All the functions are static, and all the relations between modules are of type usage. Table 2.1 summarizes Theo's perception. Tip: the only kind of relation between DOP modules is the usage relation. Tip: each part of a DOP system is easy to understand because it provides constraints. Section 2.5. DOP systems are flexible. Theo, I see how a sharp separation between code and data makes DOP systems easier to understand than classic OOP systems. But what about adapting to changes in requirements? Joe, another benefit of DOP systems is that it is easy to extend them and to adapt to changing requirements. Theo, I remember that when Nancy asked me to add super members and VIP members to the system, it was hard to adapt my OOP system. I had to introduce a few base classes, and the class hierarchy became really complex. Joe, I know exactly what you mean. I've experienced the same kind of struggle so many times. Describe the changes in the requirements for super members and VIP members, and I'm quite sure that you'll see how easy it would be to extend your DOP system. The requirements for super members and VIP members. Super members are members that are allowed to list the book lendings to other members. VIP members are members that are allowed to add book items to the library. Theo opens his IDE and starts to code the Get Book Lendings function of the library module. See listing 2.3. First, without addressing the requirements for super members. Theo remembers what Joe told him about module functions in DOP. Functions are stateless. Functions receive the data they manipulate as their first argument. In terms of functionality, Get Book Lendings has two parts. Checks that the user is a librarian, retrieves the book lendings from the catalog. Basically, the code of Get Book Lendings has two parts as well. Calls the isLibrarian function from the user management module and passes it the user management data. Calls the Get Book Lendings function from the catalog module and passes it the catalog data. It's Theo's first piece of DOP code, and passing around all those data objects, library data.usermanagement, and library data.catalog, feels a bit awkward. But he did it. Joe looks at Theo's code and seems satisfied. Joe, now how would you adapt your code to super members? Theo, I would add a function isSuperMember to the user management module and call it from library.getBookLendings. Joe, exactly. It's as simple as that. Theo types the code on his laptop so that he can show it to Joe. Here's how Theo adapts his code for super members. Now, the awkward feeling caused by passing around all those data objects is dominated by a feeling of relief. Adapting to this change in requirements takes only a few lines of code, and